So here's problem 1 from week 3 of the building construction class. And you can see the scenario here is that we have two coplanar forces, which means that basically we're just working in a two-dimensional plane. We don't need to consider any third direction. There's no force coming out of the screen or going into the screen. Everything is left and right and up and down in this diagram. And you'll notice that they're showing a 200-pound force to the right and a 400-pound weight. Well, a weight is simply a force downward. And we're being asked to calculate this angle theta as well as the tension in this cable or wire rope that's going from point A to point B. Well, you know, there are a few things we can figure out just kind of intuitively. One is that I know that point A has to be have an upward force of 400 pounds. And it has to have a leftward force of 200 pounds. And this is just simply a matter of conservation of forces. If you read the materials on static equilibrium, you'll probably recall encountering a formula that looks like this and a formula that looks like this. And the way you'd say this is sigma f of x equals 0. In fact, we could actually make this 3 bars to say must equal 0 or is identically equal to 0. And the same thing here for sigma f sub y. Well, f sub x means forces in the x direction. So if you think about our Cartesian plane here, it means forces left or right. So forces in the x direction, or we could make a note that means left or right. Now, sigma just means add up all of them. So what does it say? It says, look, if I add up all of the forces pulling to the left and the right, they have to equal 0. So here I have a 200-pound force to the right. I could think of this 200-pound force to the left as being negative 200. 200 plus negative 200 adds to 0. And so I know that the force at point A has got to be a 200-pound leftward pull. Same thing with f of y, right? F of y are forces in the y direction. And we could think of that in our note as up and down. So, if the weight is pulling down on the wire rope with a force of 400 pounds, the equal and opposite reaction has got to be that the wire rope is pulling up on the weight with a force of 400 pounds. Now, what we can do is we can treat any point within the diagram, because this is static, as kind of the center of a free body diagram. So if I make point B the center of a free body diagram, well, I can draw in the wire rope's leftward force. The wire rope's got to be pulling to the left with a force of 200 pounds, and its upward force with a force of 400 pounds. And by definition, this corner is 90 degrees, even though it doesn't appear that way in the drawing, because I've stated that forces in the y direction are vertical and forces in the x direction are horizontal. Now the question, there's two questions. One is, what is the tension in wire rope AB? Well, the tension is equivalent to the length of this side, this hypotenuse, I should say, of this right triangle here. So, to find tension, well, tension is going to equal, actually tension squared is going to equal 400 squared plus 200 squared. How do I get just tension? Well, I take the square root of both sides. So square root of that's going to give me tension. Square root of this sum is going to give me the actual number. So let's run the number on that. 400 squared plus 200 squared equals, and then I need to raise that to the 1/2 power to take its square root. So the tension in the wire rope is about 447 pounds. Now, you could ask, is that reasonable? Well, it is reasonable. It's reasonable in the sense that it's on the same order of magnitude as the weight, but it is more than the weight. If you think about, if we allow everything to relax here, basically if we took away this 200-pound force, this wire rope would hang straight vertical, and the tension would be 400 pounds. But we aren't letting everything relax. We're pulling the weight to the side with a force of 200 pounds, which means the tension in the rope has got to be that 400-pound vertical element plus whatever sideways force we applied to it to get the weight to displace this distance, which in this case would be 200 pounds. So it needs to be more than 400, but it's not going to, for instance, it's not likely to be 4,000 or 40,000. It's going to be in the vicinity. Now the other thing we're asked to find is this angle theta. Well, that's not a real clean problem, but what is a clean problem is finding this angle, which I will label as angle alpha. So we're trying to find angle alpha, and we know the side adjacent to angle alpha and the side opposite to angle alpha. So let's think about our trigonometric functions. Again, it's SO, CA, TOA. And which of these functions relates opposite and adjacent? Well, it's the tangent function. So what do we know? We know the tangent of angle alpha equals opposite over adjacent, 400 over 200. But remember, the way the tangent function works is you put an angle in and you get a ratio out. And here we know a ratio and we're trying to find the angle. So we have to use the untangent function, the inverse function of tangent, which we call the arctangent. So arctangent of 400 over 200 is going to give us angle alpha. So, well, 400 divided by 200, that's simply 2, so we don't need to put all of the numbers in. We can just put 2 inverse. That gives us the arctangent key, and we're operating in degrees mode. So the included angle inside the triangle is about 63.4 degrees. So let's write that in. That's what alpha is, 63.4 degrees. And we could draw that in here, 63.4. Now, what helps us out is this property of this identity of similar angles, that by definition, this vector with the 200-pound tension in it is parallel to this surface, which is referenced to angle theta. And that's because this is given as a horizontal surface, and the 200-pound vector is purely x, which means that by definition it's horizontal. Well, under those circumstances where we are able to say that this line is parallel to this line, then these included angles will be identical. So that angle theta has to be equal to angle alpha. So all we have to say is that angle alpha equals angle theta. And there we've derived the answers that they were looking for. That theta is 63.4 degrees, and the tension on the wire rope is 447 pounds.